Welcome back to eCoreAcademy, everyone. My name is Anita Raj, and I am one of the co-founders here along with my younger brother AJ Raj. As you can see, I'm also the teacher of Biology 1 here at eCoreAcademy, and today we're going to be covering a new lesson which is called Properties of Water. Since this is part 3, for those of you who haven't seen my other 2 parts, there are 2 other parts that exist. The part 2 is going to be linked in the description box, but to find all 3 parts organized sequentially, you can go to our YouTube channel and you can find the whole Biology 1 playlist. So not only will you have access to Properties of Water, the 3 videos, you'll have access to all the Biology 1 videos I've done so far. So now talk about high specific heat. Let's talk, like I said before, the term is specific heat, but I wrote high specific heat because water has high specific heat. So first, let's talk about what just specific heat is. It's also known as specific heat capacity because it's going to talk about capacity is like the amount. So, for example, if my mental capacity is very high, that means I'm smart. I can retain a lot of information in my head. So that's just what capacity means. So let's talk about what specific heat means. So specific heat is the amount of heat 1 gram of liquid must lose or absorb to change temperature by 1 degree. So here's my example. If you have 1 gram of water and it's at 79 degrees Fahrenheit and you want to see how much heat you must add or how much heat you must take away to change that temperature by 1 degree, to change that temperature either from 79 degrees, by adding heat you get to 80 degrees, or by taking away heat, you get to 79 degrees. It's going to be constant whether you add or take away heat. You're just trying to find out how much heat, how much, like that unit of heat. You're trying to find out how much heat you need to add or take away so that you can change that 1 gram of water by 1 degree Fahrenheit. So that's what specific heat is. We'll talk about how water has high specific heat. It has the highest specific heat, actually, of any liquid at 4.184 joules to raise the temperature of 1 gram of water 1 degree Celsius. So 4.184 joules is pretty high. Like we said, water is the highest specific heat of any liquid, and you need to add or take away 4.184 joules of heat from water if you want to change water's temperature by 1 degree Celsius. So my example, actually, when I talked about the 79 degrees Fahrenheit, I should actually say it as 79 degrees Celsius because just keep in mind that we're going to be talking in terms of Celsius, but I will also say in degrees and in terms of Fahrenheit, just for all the viewers who use that form of measurement. But in this case, for example, if we had 1 gram of water, like we were saying, we would have and let's say it's at 79 degrees Celsius. If we want to heat that water, if we want to get that water to 80 degrees Celsius, we're going to have to add 4.184 joules of heat so that we can get up to 80 degrees. If we want to get that water down to 78 degrees Celsius, meaning we want to decrease it by 1 degree Celsius, we're going to have to take away 4.184 joules of heat. So heat of vaporization is pretty much the amount of heat you're going to have to add to a liquid to change it to a gas. Hot specific heat is just how much heat you're going to have to add to a liquid to just make it hotter. So in this case, we're not trying to turn liquid water into gas. We're just trying to make liquid water itself hotter. So that's the difference. Again, this is due to hydrogen bonds. So let's talk about exactly how it's due to hydrogen bonds. So think about it again. It's literally the exact same concept. So hydrogen bonds, when the environment gets too hot, they'll absorb the heat so that the water molecules don't get hot too fast and the environment can gradually get hotter. However, when the environment cools, hydrogen bonds are going to release heat so that the water molecules remain a bit hotter so the environment doesn't quickly get too cold for the organisms. So that's all due to the hydrogen bond. So if you have a body of water in an ecosystem, what it's going to do, it's pretty much going to be essential to life, like we say, because if the environment gets too hot, what's going to happen is the hydrogen bonds in the liquid are going to absorb the heat in the environment, but they're not going to change into a gas yet. The water will still be water, but the hydrogen bonds are going to absorb the heat so that that body of water, let's say it's a lake, the lake actually helps the ecosystem cool down, and it doesn't evaporate. The water doesn't evaporate in this case. The adverse is also true. So if you have a environment and it's super, super cold, the hydrogen bonds are going to release heat, but the water itself is not necessarily going to freeze. So the surface usually freezes, like some of you have seen lakes freeze over, the surface freeze over, but all the water underneath it's still very dense and still very hot at around I think water is dense at 4 degrees Celsius, but it's still it's still suitable for organisms to live in. So that's how specific heat works. So liquid, how much how much heat you need to add to a liquid to just simply make the liquid hotter or colder, or how much energy you have to add or take away. I should say that. So again, this is essential to life because organisms are not good with like sudden temperature changes. We have to have gradual temperature changes, because I didn't explain this fully why that's necessary, but we'll talk about it later on when we talk about enzymes. You've all probably heard about enzymes. They help with chemical reactions and metabolism in our body. So how we pretty much convert the food we eat into fuel so that we can still run, so that we can still live. If the temperature is too extreme, or if it's just fluctuating too much, what's going to happen is those enzymes are going to become denatured, meaning they're not going to work anymore. And if they don't work, we're not going to have the energy we need to live. So that's why temperature is super important. And if temperature is too extreme, our organ systems are going to fail, etc., etc. So that's why organisms need very gradual temperature changes so our bodies can adjust. Again, like, because it takes a lot of energy to heat and cool water, temperature changes are gradual, which is what we need. They're resistant to temperature changes because hydrogen bonds are always going to release heat when it gets too cold, so it counteracts that. And then they're going to absorb heat when it gets too hot, so that the environment can stay a bit cooler. So it's going to oppose that. So it's always going to do the opposite. So hydrogen bonds and water molecules are always going to do the opposite, so that the ecosystem and the organisms don't experience great fluctuations in heat. And this gives time for the organisms to adjust to the changing temperature, like we talked about. We're good with gradual temperature changes because we can adjust. However, if they're way too sudden, that's when the problems happen. Okay, so let's look at some heat visuals. So this up here is where it's raining. So I'm just quickly going to run through these. So rain comes from the cloud. Remember, the water molecules in water vapor are going to condense and become liquid water, and they're going to fall to the earth as precipitation in the form of rain. What's going to happen is this is actually going to keep the environment a bit hot, because even though this water is falling like on the ground, on the flowers, even though it is chilly, what's going to happen is, because the environment's getting a bit colder, the hydrogen bonds in the water molecules in these water droplets are going to release heat so that the environment doesn't get too cold. Here you're going to see a field on a very hot summer day, and you see like steam coming off of the field. So this is actually water vapor. The water vapor is, so there's liquid in, obviously, probably the roots of these plants, in these plants themselves, and it's evaporating because it's just so hot. Remember, high heat of vaporization, so it's probably so hot to the point where the liquid water in the plants is turning into water vapor. But what happens is, because it's so hot, the water molecules are going to actually have their hydrogen bonds absorb the heat from the sun, so that the plants don't get too hot, so that they actually stay a bit cool. And that's how the water vapor here is going to help. Here we have a iced over lake, so this has more to do with specific heat. So the water at the top is going to be very cold. It's going to be like we talked about the ice crystals in the last video. So it's going to ice over, but right beneath this, it's usually a thin layer. Right beneath it, we're going to have liquid water. And in the last video, we talked about how solid water, which is ice, is actually less dense than liquid water, which almost never happens. Usually the solid form of any element or compound is denser and heavier than the liquid form, but that's not true for water. And the reason that's important is because organisms will actually live beneath the surface. So If ice was denser than liquid water, then all the ice would sink to the bottom of the lake and it would just pile up in layers and organisms wouldn't be able to survive. But because beneath this sheet of ice there's hot, dense water, for around 4 degrees Celsius, which is hot for some organisms because it's freezing in the winter. That's a luxury itself. That helps organisms stay alive. And that's specific heat for you because it's the water molecules are releasing heat from their hydrogen bonds. They're not changing state. They're still remaining liquid, but they're making the environment more suitable for organisms. And here we have a jungle. It's very similar to this, the field, because a lot of times you'll have moisture and dew on the petal, on like leaves and petals of the different exotic plants. But these jungles do get very hot, so rather than having all the trees dry out and just burn in the sun, water will evaporate. So that's the example of heat of vaporization. And when it evaporates, hydrogen bonds are going to absorb heat so that and absorb heat from the environment, so the environment could cool down. Okay, so moving on to universal solvent. So why is water a universal solvent? I'll just show you everything on this slide. So water is considered a solvent for life because of its versatility and polarity. So it can dissolve polar and ionic molecules which are charged. I'm going to come back to that. I'm going to first review what a solution, solvent, and solute are. So remember, a solution is a type of mixture. A mixture is where different components are not chemically bonded together. So solutions can be separated by different methods. For example, evaporation, distillation, formation of a precipitate, things like that. So solutions are types of mixtures, but they're uniform mixtures. So you can think of them as I can't think of the word, it starts with homo, but they're same throughout. So for example, a typical mixture that your teacher might talk about is trail mix. So a bunch of peanuts and almonds and all that good stuff. There you can see the different parts of the mixture and you can actually separate them. They're not chemically bonded together. That's why they're a mixture. But a solution is also another type of mixture because you can separate the components, but everything is mixed together, so you can't tell one thing apart from another. So it's usually a mixture of two substances, one of which has been dissolved in the other. So what the substance that has been dissolved in the other is called the solute. So I'm going to jump down here. Solute is what is being dissolved. The substance in the solution that does the dissolving is called the solvent. So solvent does the dissolving. For example, here I forget what substance this is, but this isn't water, it's some other substance, and these are M&Ms, and M&Ms have dye on them. So what's happening is whatever substance this is, the liquid they're sitting in, I don't know why it's slipping my memory, but it's actually acting as a solvent, so it's going to dissolve that dye on the M&Ms. That's why the M&Ms are bleeding. So the dye is the solute, is what's being dissolved, and whatever liquid they're sitting in is the solvent. It is what is dissolving the dye. So this altogether would be considered a solution. Down here we have, I believe, oh my god, I can't remember. I believe this is salt. This is salt. So salt is being poured into a beaker of water. Taking a note that we're calling this the universal solvent. Water is a universal solvent. Remember, solvent is what's doing the dissolving. So water is not being dissolved. Water is what's doing the dissolving. So water in this case is the solvent. A spoon is dumping salt into the water, and what's going to happen is after you stir it a bit, this salt is going to be dispersed throughout the water to the point where you're not even going to be able to tell. You're not even going to be able to see a salt a particle of salt apart from a water molecule because it's going to be dissolved in it. It's going to be uniform. You can't see one from the other. And you've probably already seen this when you put sugar in water, because sugar also gets dissolved in water when you put salt in water. So water is considered the solvent for life. It's called a universal solvent. When we think universal, we think like everything. So water is super versatile because it is known for being able to dissolve almost all substances. Not all, but almost all substances. And it's essential for life because of this. I'll talk exactly about why it's essential for life. So common names are universal solvent because they can dissolve almost anything, and solvent for life because its properties as a solvent actually work in our biological systems. And again, I'll talk about how it works in our body, in the bodies of different organisms as well. And it can dissolve polar and ionic molecules. So ionic molecules are charged molecules. For example, like sodium chloride, like sodium chloride, which is NaCl, which is salt. So it can dissolve polar molecules. Other polar molecules include ammonia, things like that. It can dissolve Water can dissolve them because remember, like dissolves like we talked about in the last video. Yes, like dissolves like, so water can dissolve other polar molecules. Can also dissolve charged or ionic molecules like NaCl, sodium chloride, those four, sodium and chlorine form an ionic bond, so they are ionic, so water can dissolve them as well. So examples of why water is considered the solvent for life, why it's important in our biological systems, is just think of water and salt, honestly. I think it'll be easier to explain it this way. So how exactly does water dissolve? Just something basic like salt, and then you can apply it to how it dissolves more complicated, complex molecules in our body. So water and salt. Like we said, the hydrogen of a water molecule is partially positive, and the oxygen of a water molecule is partially negative. In salt, the sodium is positive because it lost a electron, so it has more protons than electrons. And then the chlorine is more negative because it gained an electron, so it has more electrons than protons. So what's going to happen is the hydrogen, which is partially positive in the water molecule, is going to be attracted to the chlorine ions, or chloride, which are, remember, anions, which have a negative charge. So the hydrogen, which is positive, is going to be attracted to the chlorine, which is negative. And then meanwhile, oxygen, which is negative, is going to be attracted to the sodium, which is positive. So the two different parts of each of these each of these substances are going to be attracted to each other, and that's what makes salt actually dissolve in water, because of that attraction. So it's also a main solvent in cells, blood, and plant sap. So water is found in high concentration in like the cytoplasm of the cell, which is this jelly-like substance, which holds all the organelles. If you look at plant cells, actually, plants rely on water so much. Plants are able to actually stay upright because of turgid pressure. We're going to be talking about it later on, but that's because the plant cells are literally bloated, like literally filled with water. So that's considered a healthy plant cell if it's just filled with water, because water is actually able to dissolve all the nutrients in both cells and in any kind of cell, so that they dissolve those nutrients, so that it's easier for the cell to use. Also in blood, because blood is actually made up of the plasma in blood is actually made up of 91% to 92% water, and I think the rest of it's just made up of other things, other nutrients and things like that. And water dissolves those nutrients, and it makes it easier to carry throughout the body. And lastly, plant sap, very similar to blood in that manner. Okay, lastly, let's talk about hydrophilic versus hydrophobic. So, hydrophilic versus hydrophobic. Remember how I said like dissolves like? So, polar substances such as water are going to dissolve other polar substances. Nonpolar substances, on the other hand, are going to dissolve other nonpolar substances. However, a polar substance like water cannot dissolve a nonpolar substance. We'll talk about examples, but all throughout this, I want you to remember that like dissolves like. So hydrophilic means water loving. Hydro means water, philic means loving, water loving. So any molecule that is hydrophilic is water loving. Because it's water loving, it must also be polar, or ionic, or charged. This means it can be dissolved by water, like we said, salt or sugar. It can be, if we put it in water, water can dissolve it. It'll be mixed through water. So when we look at water after mixing it, you can't tell like the salt or sugar molecules apart from the sugar particles apart from water. Because they are charged or polar, they are like water. They like water because of that, because they are similar to water. These are, like I said, ionic and polar molecules like salts and sugar. And we explained that on the last slide on exactly why water dissolves ionic and polar molecules. However, we also have hydrophobic molecules. So hydro means water, but phobic means fearing. So if you ever heard of phobia, it means like a type of fear, like arachnophobia, fear of spiders or arachnids, and genophobia, which is fear of knees. Don't ask me how I know that. I do a project on it, but phobia just means fear. So these are going to be molecules that fear water, just don't like it. Remember how we said nonpolar molecules are what dislike water. They just don't mix with water well. And this is because water is a polar molecule, and polar molecules are molecules in which one part of the molecule is partially negative and one part of the molecule is partially positive. So the electrical distribution is not even. It's imbalanced. But in a nonpolar molecule, it is balanced. So overall, the molecule doesn't really, so it's balanced. So it won't have that one side that's negative, one side that's positive, like a water molecule, and that polar and nonpolar. That's why those kinds of substances just don't clash well. Just clash. They don't go well together, and because of that, they cannot be dissolved by water. Like they're not compatible with water. If you want to think of that. They can be dissolved by other molecules such as lipids, however. So lipids are fats. We'll look at them later on, but lipids are fats, and lipids are actually nonpolar. So unlike water, they are nonpolar. We'll talk about that later on. But let's talk about just generally hydrophobic substances. Because they're hydrophobic, they don't like water. They can't be dissolved by water because like dissolves like. However, lipids, which are also hydrophobic, which are also nonpolar, can dissolve other hydrophobic molecules. So hydrophobic molecules like hydrophobic molecules, meaning same thing, nonpolar molecules can dissolve nonpolar molecules. And examples of such nonpolar molecules are oils, waxes, and other fats. So in this picture up here, this is actually sugar. The last one was salt on the other side. This one is sugar. Someone's dumping it into water because sugar can be dissolved in water because it's a polar molecule. However, this up here, you've actually probably seen this, is oil. You've probably seen this in other classes. Like I remember I did a lab on it in like 6th grade. And we all know that oil just doesn't mix with water. Oil will sit on water because it's less dense than water. It doesn't mix with water because it can't be dissolved in water. And it can't be dissolved in water because it's nonpolar, meaning it's hydrophobic. But if this water, for example, was a fat or an oil, a fat or a wax, this oil would be able to mix with it because remember, like dissolves like. So the nonpolar substances would be able to dissolve in each other. So that's all I have for you today. I hope you enjoyed this video. Last one on water molecules. I know we're going to miss them, but we're ready to move on. If you enjoyed this video, please hit the like button, subscribe button, post notification bell, drop a comment down below, and share it using our social media shown here. You can also email us at eCoreAcademy@gmail.com if you have any questions or anything at all, honestly. And lastly, please check out our website when you can for all the additional resources. Have a great day and see you in my next biology video.